Hello everyone, Dominik and I will take the next 10 minutes to talk about our paper with the title Digital Decision Support in Construction, Analysis of Information Requirements and Data Provision for AI-based Selection of Sustainable Building Products. The presentation is structured as following. I will tell something about the research project, then the motivation, the method, the results, and at least the conclusions. So Dominik and I came together for a research project where we're developing an AI-based tool where we developed an AI-based tool that supports the decision-making for sustainable products. Dominik is a research assistant at the University of Wuppertal, and I'm a project manager for sustainable construction working for Eco. Our motivation: the construction industry has a high impact on the global energy demand and global greenhouse gas emissions. So it accounts for 32% of global energy demand and 34% of greenhouse gas emissions, and only the production of the building materials its account for 14% of global greenhouse gas emissions. That's why different regulation and certification systems were implemented in the last years. On the EU level, for example, we have the EU Taxonomy. On a German level, we have different certification systems like DGNB, that is similar to LEED or BREEAM, maybe some of you know that, or we have different funding programs like Q&G. And yeah, to meet all these regulations, the planner have to implement sustainable products in the planning process. The current challenge by implementing the sustainable products is the lack of comparability. There is no standard how the information should be provided, and so we got different data sheets for the products, like product data sheet, sustainable data sheet, or environmental product declaration, and it's really time consuming to get the right information. So we got the research question. How can existing unstructured data be used to support decision-making for sustainable building products? And we developed a method that is consisting out of 6 steps. I will just give a short introduction in the method, and Dominik will give a deep dive after step 3. So first step is the web scraper. We downloaded automatically the documents from the internet, like product sheets, technical data sheets, and environmental data sheets. The second step is the document processing. So there was a transformation from the PDF format to processable format like Excel. And the third step is the product classification via large language model based on classification systems for products. The large language model defined the product, and depending on the product type, and text extraction using LLM and LangChain was following. And yeah, the extracted data we got in JSON, then a validation loop confirmed the results. And in the 5th step, we paired the product information out of the documents in JSON with the predefined sustainable requirements that are also in JSON. And the 6th step was the knowledge graph with Neo4j.
Now we want to take a closer look to step 3 to 6. To extract the relevant product information from the documents, we first need to tag each product-related document with the correct product type. For that, we are using a vector database and the API of ChatGPT is for our mini model. Starting with the vector embedding similarity search, followed by a chain of thought prompt with the following 4 steps. First, analyze the text in the documents. Second, match them against the product type definitions, like shown here at the top. Third, check if the embedding guess is a good fit or not. And the last step, if needed, correct the decision and give out the final product type. Depending on the product type, the LLM then extracts the defined properties and stores them into a JSON file like shown on the right. In our first test, we ran 29 products with a lot of documents and captured 208 technical and social-cultural properties. The eco data from the environmental product declaration are extracted via simple regex. For that, no LLM is necessary. The reliability is logged in with a validation loop, up to 10 repeats, stopping after 2 identical results in a row. For the 208 properties, we obtained a confidence score of 0.986, which means that only 3 of the 208 properties had to be checked manually of the user. In step 5, the product data is compared with the requirements of the different sustainable systems, like Karina said, the EU Taxonomy, DGNB, and QNG. We also translate the requirements into a JSON file. So in the next step, a Python script can automatically check things, like is the VOC content of our product lower than the limit for the product type. With the same Python script, we store the product information and the sustainability requirements in a structured way in a knowledge graph. In our case, it's Neo4j. In this way, we get the 29 building products across 12 different product types and gained 65 unique property names. The color code keeps it clear. We have the turquoise one is the main building product. Then we have in orange technical information, ecological information, economical information. In purple, socio-cultural information, and in red, the documents where the properties are extracted from. The pink nodes on the right side represent the product classification, including which product type they belong. The building products are also linked to each other via these pink nodes, creating a large current network of information. So here's just shown one of the 29 building products. Important, if the building products fulfills the requirements of a system like shown in step 5, a link is automatically created between the building product and the requirements with the relationship fulfills requirements of. What results did we achieve? Thanks to Cypher, the query language of Neo4j, we can ask complex so-called multi-hop queries like which sand lime brick, that's the product type, with the compressive strength over 12 Newton per square millimeter and a thickness of 200 millimeter has the lowest global warming potential. Or second question, which adhesive fulfills quality level 3 of, for example, DGNB criteria. These multi-criteria questions would be a nightmare to a normal spreadsheet, but our knowledge graph can answer them in seconds. What are the big takeaways? We receive a high automation with a confidence score of 0.986. We have 90% less prep work for our data. The knowledge graph gives us transparent, traceable decisions, but the biggest bottleneck is the documents of our products don't provide any price information, which is why the economic factors cannot be taken into account this way. But in the meantime, We developed a graph rec pipeline with a web UI that turns natural language into Cypher and queries the graph in real time. It's a digital decision support system that weighs sustainability, technical and sociocultural factors at the press of a button. And you can plug in your own cost data to cover the economic side too. Wrapping up, we built a digital decision support system that delivers transparent, efficient and scalable material decisions in construction. Thanks for listening.